Okay, so here's another problem regarding computing areas enclosed by functions. And in this case, we're given four functions. We're given y is equal to 1 over x plus 2, y is equal to x plus 2 squared, x is equal to negative 3 halves, and x is equal to 1. Now, the first thing that we want to do is obviously we want to graph this so that we can get an idea of what area we're calculating. And one thing that we're going to notice is that this area itself is constrained by these two x functions. So the fact that x equals negative 3 halves is just a vertical line at negative 1 half, and the fact that x equals 1 is just a vertical line at x equals 1, tells us that we're going to be computing the integral from negative 1.5 all the way to 1. Now, there are a few things that we have to keep in mind when we're doing this, namely the fact that our functions change in terms of whether they're upper or lower at some point here, which we're going to have to calculate very soon in order to continue the problem. And in fact, that's our first step. So what we're going to do is we're going to set the y functions equal to one another, or in other words, we're going to set 1 over x plus 2 equal to x plus 2 squared. Now, we simply multiply both sides by x plus 2 to get rid of this denominator, and we're left with 1 is equal to x plus 2 cubed. We'll go ahead and take the cubed root of both sides, and we'll find that 1 is equal to x plus 2, or in other words, x is equal to negative 1. Now, this value right here tells us where these two functions intersect, and it happens to be at x is equal to negative 1. I'm sorry that it's not drawn to scale, but you'll note that this point right here is, in fact, x is equal to negative 1. And now that we know this, we can actually begin to solve this integral, but we have to keep in mind that, again, we're going to be using two integrals to solve this because the upper and lower functions change depending on where you are along the x-axis of this function. So for the first part of our integral, we're going to compute this area right here, and the upper function is going to be 1 over x plus 2, and the lower function is going to be y is equal to x plus 2. So I've noted that down here. The upper minus the lower function is what gives us the area between this curve, and we know that these two functions intersect at negative 1, which tells us that we're going to be computing the area from negative 1.5 to negative 1. And for our second part of the integral, or our second integral, we notice that our upper functions and our lower functions change because what used to be the lower function now becomes the upper function, or our upper function now becomes y is equal to x plus 2 squared, and our lower function is equal to y is equal to 1 over x plus 2. And when we do that, we get this nice integral over here from negative 1 to 1, which is actually determined by our second constraint x function right here, which we've graphed as a vertical line at x is equal to 1. So once we've computed these integrals, and they're actually fairly simple because whenever you have something in the denominator like this that isn't squared, we can go ahead and take the ln of the absolute value of that value of this function right here, and because this is because this would be technically a power rule, we'll just use the power rule of integration to solve, and what we get is that this integral is equal to the ln of the absolute value of x plus 2 minus 1/3 times x plus 2 cubed. And of course, we have to use the fundamental theorem of calculus to find the actual area, in this case from negative 1.5 to negative 1. And it's the same case with this function over here. When we do all of the integration, we're left with 1/3 times x plus 2 cubed minus the ln of the absolute value of x plus 2, and this is going to be from negative 1 to 1. You'll notice that we got the same answers here, except the order in which they appear is switched because of the fact that the upper and lower functions switch here. But effectively, you're solving the same integral twice. So I went ahead and I broke this down into a left side and right side solving method because it can get kind of messy and kind of long. And I know it's still got kind of messy and long, but I just feel like it was more organized this way. And really what I did was I plugged in this this top number here everywhere that I saw x first, and then I subtracted that by the same function, except for x I'm plugging in -1/5. And once you do all of the calculations, you can solve this algebraically, but since the answer is trying to, since the answer is going to include some decimal points, I figure it's actually, it can actually be beneficial to get an idea of what the answer is in terms of decimals. And once you do all the solving, the left side of the integral gives us an area of 0.40148. And now on to the right side. So for the right side, we're going to do the same thing, except we're going to use this function over here, and we're going to plug in 1 first, and then we're going to plug in our -1 and subtract that by the first function. And once all of that is done, we'll get an answer of approximately 7.56805. Now, you'll have to recall that the entire point of this is to add these two areas together in order to find the total area that's enclosed by these two functions here. And when we do that, when we add these two numbers here, 0.40148 and 7.56805, we get a final answer that is equal to 7.96953.